If we wanted to go into business making resistors, we need to know how R is determined. Just like with capacitors, it depends on both the material that we use and the geometry. The material property that's important is known as resistivity, not resistance, and its units are ohms times meters. We know that copper is a better conductor, meaning much lower resistivity, than glass. The other important factors are area of the resistor and its length. Here, thinking about water pipes helps again. A large diameter pipe gives less resistance to the flow of water than a small diameter pipe, and it takes more power to pump water 100 meters down a pipe than 10 meters down a pipe. If we assume our resistor is shaped like a cylinder, our equation is just resistance in ohms is the material property resistivity times length divided by area. Now, there are special materials known as superconductors that have zero resistivity, but we need liquid nitrogen temperatures to make that happen. At room temperature, the best conductor is silver with a resistivity of 1.59 times 10 to the negative 8 ohm meters, then copper at 1.68 times 10 to the negative 8, and then gold. Those are the best three. If copper and silver are better conductors than gold, why are the connectors for things like USB cords and computer cards gold plated instead of plated with silver or copper? Well, you can see the reason in these pictures. Silver will tarnish and so will copper, but gold doesn't. Anyway, most metals have resistivities that aren't far from this, roughly 10 to the minus 8 ohm meters. Semiconductors, like we use in computer chips, have values from 10 to the minus 5 all the way up to maybe 10,000, depending on what they're made of exactly. Glass can go from 10 to the ninth to 10 to the 14th. Quartz and rubber, you go somewhere 10 to the 16th, 10 to the 18th. So there's a huge range between the best conductors, even not superconductors, and the best insulators. 26 orders of magnitude. That's a factor of more than a trillion trillion. It'd be hard to find a physical property with a greater range. Now, there is some temperature dependence on this material parameter. In general, for most things, resistivity goes up with temperature, but not very fast. We're going to ignore it because the resistors that people use for electronic circuits, we don't usually want them to change much over a given temperature range. They would be better as thermometers than resistors if that's the way it worked. And that is one way to make a thermometer. We're just going to consider rho to be constant for a given material, not a function of temperature. In a circuit diagram, we draw the resistor like a zigzag. So here in this circuit, we have two batteries and three resistors. V equals IR tells us how the current, voltage, and resistance are related, but we also, a lot of times, want to know about the power that a circuit consumes. From last semester, we know that power is the change in energy per time, or the rate that work is being done. We know that the work associated with moving a charge through a potential difference V is just Q times V. We can write the power as delta W over delta T, and if we're moving many charges per unit time, we could write it as P is delta Q over delta T times V. Now, with our definition of current, that means we could write this as just P equals IV. For example, if we go back to your car starter again, maybe it draws 300 amps. If the battery is maintaining a potential difference of 12 volts, and it's usually closer to 14, the power is going to be 300 times 12, or 3,600 watts. If we have a circuit with just a resistor and battery, we could rewrite P equals IV a couple of ways using Ohm's law. We can use V equals IR to replace the voltage and get power as I squared times R, or we could replace I with V over R and write it as V squared over R. The power consumed in a circuit is useful to know because we can figure out what the circuit will cost to run. The power company bills us based on the number of kilowatt hours we use. 1 kilowatt hour means 1,000 watts, or 1,000 joules per second, for 1 hour. So 1,000 watts times 3,600 seconds is 3.6 million joules. In most places in the U.S., this is somewhere around 10 cents, depending on other things like industrial customers get a better deal than residential. Usually it's more expensive in the South in the summer than the winter, etc.